So, definite integrals with linear motion, okay? When you were first introduced to linear motion, you were introduced using derivatives, okay? We talked about displacement. When we took the derivative of displacement, that gave us what? Velocity, and then we took the derivative of velocity, that gave us what? Acceleration. And so now we're going to use definite integrals to work our way backwards. So in these types of problems, you're going to learn how to find displacement when given velocity or when given acceleration to begin with. And you're also going to learn how to find the distance traveled of a particular particle, okay? The distance traveled. So to refresh your memory, the displacement function tells us the distance and direction a particle is from an original origin at a particular time. When we take the antiderivative of velocity from one time, t1, to another time, t2, remember the antiderivative means we're going backwards. So if we're given velocity, and we take the antiderivative of that, we get displacement. And if we evaluate it, since it's the definite integral, we plug in t2, we subtract it from when we plug in t1, we're able to find the change in displacement from our first time to our second time. So the change in our location between one time and another time, okay? This is used in projectile motion, engineering, and things like that. Now, this you don't necessarily have to write down. I'm just trying to make sure you guys understand it. I know it looks kind of blurry, so I do apologize for that. Let's say you're given a displacement function, t to the second minus 4t plus 3. If I plug in 0 into the displacement function, I get 3. This tells us that at 0 seconds, so wherever we initially start timing, the particle is 3 meters to the right of its original starting place. When we plug in 2 for t, remember t represents our time. So, and we plug in 2, we're at -1. That means at 2 seconds, our particle is 1 meter to the left of the origin, okay? So, if this represents the origin, then at 0 seconds, we're at 3 meters, okay? So this is where we would start. But then at 2 seconds, we're at -1, okay? So we went back this way in that direction for 2 seconds, all right? What am I drawing right here? Who remembers the name of this? We did this in derivatives. Like if I found S of 5, I could probably, probably would tell me to go back this way to a particular point. No one remembers? You remember doing it? You don't remember what it was called? Displacement. Displacement function was 2 words. Wasn't the timeline. What are we talking about today? Linear motion. Okay, so one of those words is a part of those 2 words.
Linear function.
Not a linear function.
Was it a motion diagram?
It was a motion diagram. Yes, motion diagrams. This is when we would use our position function to plug in our respective times, and then we could determine using velocity and a few other things, whether we're going to the left or to the right, and then we create our motion diagram. Okay? Don't forget about that, because you're going to need to reach back into derivatives and motion diagrams to be able to do some of these problems that deal with linear motion and integration. Now, if we were to take the antiderivative from 0 to 2 seconds of our velocity function and we evaluated it, then we would find -4. Okay, so we take the antiderivative, we plug that in, and we'll get -4. What this gives us, again, it gives us our change in displacement between 0 seconds and 2 seconds. So it tells us that at 2 seconds, after 2 seconds, the particle is 4 meters to the left of where it originally started. The negative tells us left. If it was positive, it'd be to the right. And as you can see from this motion diagram that I drew, that's exactly true. From where I started, which was here, I'm 1, 2, 3, 4 meters away from where I originally started. Okay? That's what integration can tell us. So using that, if v is the velocity function for a particle moving along a line, the total distance traveled between one time and another time is given by this formula. The antiderivative from T1 to T2 of the absolute value of velocity, dt. So if we take the antiderivative of the absolute value velocity function, we're able to find the total distance traveled by the particle. Whenever it moves to the left, whenever it moves to the right, whenever it moves back to the left, we're able to find that total distance traveled by applying this formula right here. So that's what we're going to do. So go ahead and get down this example. We don't have too many examples today. We just have 3. So go ahead and get this one down and we'll go over it together. So displacement function for a particle moving along a horizontal line is given by the function s of t equals 8 minus 2t plus t squared, where t is greater than 0 and t is measured in seconds and s is measured in meters. We have to find the velocity of the particle at time t. Well, velocity, when we're given displacement, is nothing but the what of displacement? Is nothing but the derivative of displacement. So we have to find ds over dt, or s prime of t, to find our velocity function at time t. What would be the derivative of 8 plus 2t minus t squared? 2 minus 14.
Oh, just 2t.
It'll just be 2t. This one is not calculator. It's a polynomial function. It's going to be non-calculator. So there we go. Now it says find when the particle is moving to the right and when it's moving to the left. This here, this is derivatives. How will we determine whether the particle is moving to the right or if it's moving to the left?
Do we have to find the maximum?
And how do we do that?
Setting it equal to 0.
Okay, so it's the same process that we would do to figuring out maximums and minimums to see where it's increasing or decreasing, except this time we're just dealing with a particle that's going either left or right. But it's the same concept. So we have to set the derivative equal to 0. At that particular time, we're finding out where the particle is not moving at all. So when we do that, that'll be 2 equals 2t. T is equal to 1. So it's not moving at 1 second. So then I want to plug in a value that's to the left of that and to the right of that. But be careful. This right here is representing, this number line is representing our time, t. And t has to be greater than or equal to 0, okay? So when we plug in a value, we don't want to go past 0 seconds because it's not going to be accurate, okay? So let's plug in a value in between, and let's plug in a value that's bigger than 1, and let's see if it's going to be positive or negative. And where do I plug these test points into? We plug it into the derivative, because that's what we did if we were trying to determine whether it was increasing or decreasing. The same concept applies if we're moving to the left or if we're moving to the right, positive or negative. So if I plug in 1/2 into the derivative, is that going to be a positive number or a negative number? Positive. But if I plug in 2, is that going to be a positive number or a negative number? Negative. So then that tells us from 0 to 1 second, we're moving which way?
Right.
We're moving to the right, but from 1 second until the rest of the time, we're moving to the left.
Wouldn't it be a bracket on the 0 since it's included?
Thank you. And now we have to draw the motion diagram for the particle, okay? Refresh your memory a little bit on that one example I told you guys not to write down. So we need our motion diagram. So we have a horizontal line that represents the meters. We just have to figure out where we were when it was 0 seconds. We have to figure out where we were when it was 1 second. And then we'll be good to go from there to draw a diagram, okay? So we need to find S of 0. We need to figure out where we initially started. So plug in 0 into your original function. What do you get?
8.
You get 8. So at 8 seconds, that is where we started. And then we moved to the right for 1 second. After 1 second, where were we now? So what is S of 1? What is S of 1?
9.
It's 9. Because we plug 1 into the original. Now remember, we're plugging in these particular values of t into the displacement function because we're trying to figure out where this particle is located after those respective times. 0, where it started. 1, because remember, at 1 second, that's when the particle stopped and it changed direction. So after 1 second, it only made it to 9 meters and it changed direction. So as we can see, we started at 8, we went to the right for 1 second and we ended up at 9 meters, and then we went back to the left for the rest of the time. So this would be our sign diagram. So at t equals 0 seconds, that's where we started. And then at t equaled 1 second, that's where we were when we changed directions and went in the opposite way. And that would be our motion diagram. And that is a review of linear motion with derivatives. Questions before we do part D? So in part D, it says write the definite integrals to find the particle's change in displacement and the total distance traveled on the interval from 0 to 4. Use a graphic display calculator to evaluate the integral and then use the motion diagram to verify the results. The reason why we have to use our graphic display calculator here is when we do the total distance traveled, because that's the absolute value of the velocity function. And I haven't taught you guys how to find the antiderivative when absolute values are involved. Okay, that's for HO, not SO. So let me extend this page a little bit, give us a little bit more space. So let's write the definite integral. So I'll have my integral symbol. What are going to be my bounds?
0 and 4.
We're going to go from 0 to 4. And then we want to do it to find the change in the particle's displacement and the total distance traveled. So we're doing two different things here. We're finding the change in displacement, so then that's just going to be the regular antiderivative of our velocity function. To find our change in displacement. But to find our total distance traveled, we would do the integral from 0 to 4 of the absolute value of our velocity function. We got the 4 from the bounds that were given to us.
You just evaluate the first integral using the s of t2 minus s of t1.
Not on the interval from 0 to 4. We wouldn't be able to do that one.
Okay.
Okay, so when we do the antiderivative of this one, you guys should get -8. You should have gotten -8. Okay? And what that basically represents is that -8 tells us that from where we initially started to 4 seconds later, we are now 8 units or 8 meters to the left of where we started. Okay, after 4 seconds, that's what it means. We are 8 meters to the left of where we started. The left is represented by the negative, and of course the 8 tells us the amount. So then this here will tell us our distance traveled, our total distance traveled by the particle. We'll need our calculator for this one. Where is my calculator? Where do we access the integral? What button do we press to get the integral symbol? We got to go to math 9. So we go to math, we go to 9, and now we have to type in from 0 to 4. And now we have to get the absolute value of t minus 2t. Anybody remember where absolute value is located in the calculator? You have to press math, and you have to go over to number, and there it is, ABS. Now, some of your calculators pop up actual absolute value bars. Some of y'all just pop up ABS with a parenthesis. So you'll type in your function, and instead of using t, we'll have to use x. If yours pops up ABS with the parenthesis, you have to make sure you close it off. Okay, you have to make sure you include an additional parenthesis to close off the actual function. And then you'll put dx, and then you'll click enter, and we get 10. So that 10 represents that the particle has traveled a total of 10 meters from where it initially started at 0 seconds to where it is now after 4 seconds, okay? After 4 seconds. So we can verify this as well by finding S of 4, okay? Plug in 4 into the original function. You guys should have the original function written down. Plug in 4 into the original function and tell me what you get. You get 0. So after 4 seconds, this is where the particle is now. And if you look, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So yes, the particle has traveled 10 meters from where it initially started until 4 seconds. And as we can see from where we initially started again on our motion diagram to where we are now, that is a total of 8 meters. Okay, 8 meters. Questions? Let's take a look at this one. So in this particular problem, the velocity function v in meters per second, remember s to the negative 1 is just basically saying m divided by s, so meters per second, of a particle moving along a line is shown in the figure. Find the particle's change in displacement and the total distance traveled on the interval from 0 to 16. Now, unlike the last problem, we don't have a function here, we just have a graph that represents this particular situation. So that means in order to find any type of displacement change or any type of distance traveled, we're going to have to use the concept that we did when we first talked about definite integrals and area underneath the curve. Hopefully you see as this red line intersects the x-axis, some geometric shapes are formed. You remember when we first started talking about definite integrals, we talked about finding the area of the geometric shapes to find the area underneath the curve? Now remember that? You're going to need that concept here. So we have this first shape, which is a what? It's a triangle. I'm going to label that area 1. Then I have this next shape. What is this? It's another triangle, so I'm going to label that area 2. Now this last shape, we might differ on, but how I'm going to do it, I'm going to call this area 3, but what is it? It's a trapezoid. So when I find these respective areas for each of these regions, I'm going to use 2 triangle formulas and then the trapezoid formula. And what we're trying to do is we're trying to find the particle's change in displacement and the total distance traveled on the interval from 0 to 16. 0 to 16, okay? We can do this for the distance traveled, which is the absolute value of v of t dt. We're able to go from 0 to 16 to find the total distance traveled. But if you recall from our knowledge of integration, to find the displacement, we're not going to be able to go from 0 to 16. We have to go from 0 to what? 4, and then from 4 to 12, and then from 12 to 16. We are going to have to split it up to find the change in displacement. So we'll have to go from 0 to 4 of this velocity function, which we know is a triangle. Old school form for a triangle is 1/2 base times height. What's our base? What's our height? 4 and 4, but remember, since that triangle's underneath the x-axis, one of them should be a negative to take into account that is below, so that way we can have our negative area. And what is 1/2 of 4 times -4? -8. Online, someone do the next part. I have the integral from 4 to 12 of our velocity function. Again, that's another triangle, which is 1/2 base times height. Online, what's my base? What's my height?
Eight and 4.
8 and 4. This one's above the x-axis, so I don't have to worry about changing anything to any negatives. What's 1/2 of 8 times 4 online?
$16.
16. And now for my last bit, which is the trapezoid, that's going to go from 12 to 16. Trapezoid formula is 1/2 a plus b times our height. A and B represent the bases of the trapezoid. Anyone, what are my base lengths?
1 and 4.
1 and 4. And what's my height? -2. So then what's 1/2 of essentially 5 times a -2? -5. So then to find the total, to find our change in displacement, all we have to do is add those add those three values together. So it's -8 plus 16 minus 5, 3. So 3 meters. So the displacement of this particular particle from its starting place is 3 meters. 3 meters to the right of where it originally started. Now, of course, that's different from its total distance traveled, okay? Because distance, we know, is the absolute value of velocity. And since we found the velocity of each, since we found the integral of the velocity function for each of these regions, then our total displacement is nothing but the sum of the absolute values of each of those regions. So the absolute value is 8 for the first region, 16 for the second region, and 5 for that third region to get how far did this particle travel. Mm-hmm. 29 meters. So we can find displacement, and I wrote displacement twice. That was my mistake. This one should have been distance traveled. So we can find displacement and total distance traveled even without an actual function. Questions on this one? Displacement represents the location of the particle after a certain amount of time. So when we did it for this particular problem, we found that after 16 seconds, our particle was just 3 meters away from where it originally started. Last problem. But a culture of bacteria started with an initial population of 100 bacteria. The rate at which the number of bacteria changes over a 1-month period can be modeled by the function R of t equals e raised to the 0.273t. That is 0.273t, where R is measured in bacteria per day. And of course, t is our time. Find the population of bacteria 20 days after the culture has started. This R function, this R of t function, and the concept of displacement, velocity, and acceleration, linear motion. What does R of t represent?
Velocity.
S of t? Not quite. It does represent velocity, and the key word is right here. The rate, or keywords, the rate at which the number of bacteria changes, AKA rate of change, which represents derivative, velocity. So R of t actually represents your velocity function. So when you're trying to figure out the population 20 days after the culture has started, we need to do the antiderivative of that R of t function from what to what? From 0 to 20, okay? You definitely need to use your calculator on this one because we want to actually figure out what the population of the bacteria is, like the actual physical number, not in terms of E. So go ahead and find that out. And by doing this in your calculator, what you're finding is essentially this. Remember, the capital letter represents the original function of whatever that the integral of that velocity function is. What did you guys find that to be? To 3 significant figures, please. 858.
I got 57.
Then 57. 57.5, okay. Oh, because it was 0.49, okay. So it would be 857 because it's 857.49. So that 4 does cause it to stay at 857. But is that the total population after 20 days? Is that my final answer?
Don't you have to add 100 for the initial?
Yes, it's the initial. I have to add 100. So we started with 100 bacteria. And then the change over a 1 month period was that function. So we do have to take into account that we started with 100 bacteria. And so after 20 days, the population of bacteria is 957 bacteria. So we can apply this concept as well to application problems also. Just for your notes, in case anyone did not write it down, RFT was velocity because it was the rate of change of the bacteria over time. And rate of change indicates derivative, or in this sense, velocity. And that's linear motion, okay? Going backwards from derivatives, we go displacement, velocity, acceleration. Now we can go the opposite direction using antiderivatives, and also determining total distance traveled by taking the absolute value of our velocity function and evaluating it with respective bounds.